Hello students, Mr. Courtney here. We're going to be continuing periodic trends, and today we're going to be focusing on ionization energy, electronegativity, and we'll look at a bit of reactivity also. So we'll first start by looking at ionization energy. That is, how much energy does it take to remove the most loosely held electron? But where do we find the loosely held electrons? And the loosely held electrons, or the most loosely held electrons, will be found in the outermost energy level. And what name did we give to the electrons found in the outermost energy level? So it will be one of the valence electrons. All right, so it'd be one of the valence electrons. Okay, so let's look at the factors that help explain the trend in ionization energy. Okay, remember we looked at certain factors in the previous video. We talk about distance from nucleus, effective nuclear charge, or the ZEF, shielding effect, and electron repulsion. So we're going to start by looking at hydrogen and sodium. Now, hydrogen and sodium are in the same group. How do we know they're in the same group? Look at the number of valence electrons, number of electrons in the outermost energy level. They both have 1. Now, as we move from hydrogen to sodium, that is, as you move down the group, you see that 1, the distance from the nucleus increases. Okay. That arrow means increases. So if it increases, what would happen to the ionization energy? Ionization energy will decrease. Why does it decrease? Because the electrons, the most loosely held electrons, are further away from the nucleus. Also, as you go down, shielding effects increases, because there are more core electrons. So the shielding effect increases. So what has happened to ionization energy? Ionization energy decreases. Because remember, when shielding increases, there's less pull on the electrons, on the outermost electrons, because they are shielded by these electrons on the inside. The nuclear pull on this valence electron, or the most loosely held electron, decreases. So in summary, we can say that ionization energy decreases down a group. So if it decreases down the group, that means it becomes easier to lose the loosely held electron, because the distance from the nucleus increases. There are more energy levels between the loosely held electron and the nucleus. Shielding effect. There we have more core electrons that shield the outer electrons. There's less nuclear pull. So if we say decreases down a group, in which direction does it increase? As you go up the group, ionization energy will increase. Okay, now within a period, let's look at lithium and fluorine. How do we know that these two elements are in the same period? Look at the number of energy levels. 2 energy levels each. So what causes that difference? Okay, so if we look at it, as we move from lithium to fluorine, that is, as we go left to right on the periodic table, the ZEF, effective nuclear charge, increases because we keep adding electrons to the same energy level. So the ZEF will increase. There will be a stronger pull on the electrons. If there's a stronger pull on the electrons, you don't want to lose those electrons. Makes it more difficult to lose the loosely held electron. So that increases ionization energy as we go from left to right in a period. Okay, so as we just said, effective nuclear charge increases because we keep adding electrons to the same energy level. So that increases the effective nuclear charge, which results in a stronger pull on the electron. So that means as we go from left to right, ionization energy increases, or rather the first ionization energy increases. Now let's look at some common exceptions. Now it should be easier to remove an electron from beryllium than from boron, but it isn't. To determine why, we have to look at the electronic configuration. So this is the electronic configuration for beryllium: helium 2s2, boron, helium 2s2, 2p1. So if you want to remove an electron from beryllium, you have to be breaking up a filled s orbital. And breaking up a filled orbital is very hard to do, whereas you can simply remove one electron from an unfilled p orbital. So that makes it much easier to remove the electron from the 2p1 instead of from 2s2. So that's why the first ionization energy of boron is less than that of beryllium. More stability with the filled orbitals as compared to the unfilled orbitals. Let's look at nitrogen and oxygen now. It should be easier to remove an electron from nitrogen than from oxygen, but again, it isn't. Again, to determine why, we have to look at the electronic configuration. Nitrogen, helium 2s2, 2p3. Oxygen, helium 2s2, 2p4. As we said before, there's more stability with filled or half-filled orbitals. Nitrogen has a half-filled p orbital. Remember when we say half-filled, so let's just quickly draw an orbital diagram like this. That's what the p3 would look like. p4 would look like this. So you half-fill first, then you go back and start pairing up. So it would be easier to lose this one electron here to make oxygen 2p3 to form that ion. To lose that electron, less energy will be required to lose this electron as opposed to losing one of these electrons here. So that's why there's less energy required. Now, if we talk about multiple ionization energies, what we're talking about here is just the energy required to remove additional electron or electrons, because we're not just talking about first ionization energy anymore. So let's look at this table here. Sodium, first ionization energy is this, then it jumps to this. Magnesium, 1, 2, then it jumps. Aluminum, 1, 2, 3, then it jumps again. Look at the differences. Small differences, then a large difference. 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 And as you can see here, where we have the jump, we're getting into our core electrons. So the large jump in ionization energy is because we're going from removing valence electrons to the removal of core electrons. Remember, the core electrons will have a stable configuration, so they will end with a p6, and you're going to require large amounts of energy to break up that p6 orbital, to lose an electron from that p6 orbital. Now remember, sodium has one valence electron, so it's easy to lose that one valence electron. Then you want to lose a second electron, you get into the core electrons. Magnesium has 2 valence electrons, so the first 2 ionization energies we see are for those 2 valence electrons. Silicon would have 4 valence electrons, so the first 4 will be for those 4 valence electrons, and the 5th will be for a core electron. So, given the ionization energies for beryllium, explain the difference between ionization energy 1, 2, and 3. So, what I need for you to do now, on your note sheet, you have this, I need you to write it. You're going to have to pause the video for a bit, write out your answer, and then come back and look at the video to get your answer. It is important that you pause here, write your answer, because you guys have to do a lot more writing, and you will be required to do a lot more writing. Okay, so go ahead, pause the video, and once you've written your answer, come back and get the answer and compare it. If you need to make changes, go ahead and make the changes. Okay, so there you have your answer now. The small difference between the first two ionization energies represents the removal of the valence electrons, because beryllium has 2 valence electrons. The large difference between the second and third represents the removal of a core electron. So now we're going to talk about electronegativity. And electronegativity is how strongly an atom attracts electrons to itself. That is, how strong of a pull does an atom attract electrons to itself, especially when it's in a bond, when it's bonded to something else. So we look at it within a group first. So in the group, because we know fluorine and bromine are within the same group. How do we know they're in the same group? Again, look at the number of valence electrons. Okay, so we look at our valence electrons. Now, remember, all has to do with attraction. So what factors do you think are going to affect this? Firstly, look at the number of energy levels. So if the number of energy levels increase, then that means one factor will be the distance from the nucleus. And the distance from the nucleus increases, then we also have to look at the shielding effect. So these are the 2 factors that we're going to see within the group. So if we look at the distance from the nucleus, if the distance from the nucleus increases, will there be a strong pull on the electrons? No. So as the distance from the nucleus increases, the electronegativity will decrease. Same thing with shielding effect. We have more electrons between the nucleus and the electrons. So as core electrons increases, so more core electrons, electronegativity will decrease. So what do we see about electronegativity here? We see that within a group, electronegativity decreases as you go down the group. So that means fluorine will be more electronegative than bromine. It will have a stronger pull, it will have a stronger attraction for electrons than bromine. Within a period, so let's look within a period now. And again, how do we know lithium and fluorine are in the same period? Number of energy levels. 1, 2, 1, 2. So within the period, we have to take into consideration the ZEF, effective nuclear charge, because we keep adding electrons at the same energy level. The distance from the nucleus doesn't change. The number of core electrons wouldn't change because we're still adding them to the same energy level. So what changes is the effective nuclear charge. As we go from lithium to fluorine, the ZEF increases. So if ZEF increases, there's a stronger pull. So if there's a stronger pull on electrons, what happens to electronegativity? So that means electronegativity will increase as we go left to right. So let's summarize what we just said here. We said within a period, and we use lithium and fluorine as our examples within the period. Electronegativity increases as we go left to right, because we have an increase in the effective nuclear charge. Then we also said electronegativity decreases as we go down the group. So let's show in the trends of increase. So that tells us, if I were to ask you this now, which element has the highest electronegativity? You have to think about, why do these elements gain electrons? Why do they want to pull electrons to themselves? They pull electrons to themselves because they want to be stable. They want to gain that octet, that outer octet, that stable configuration, S2p6. Now, so which element you think has the highest electronegativity? No, it's not helium. Because remember, all these here are already stable. So we tend to ignore the noble gases. So in this case, fluorine will be our most electronegative. Okay, so fluorine is the most electronegative. The closer an element is to fluorine, the more electronegative it will be. So if you are asked to compare, let's say, sulfur with selenium, sulfur is closer to fluorine, so sulfur will have a higher electronegativity. Let's say cesium and tin, closer to fluorine. Tin has a higher electronegativity. So that's how you need to look at it. Now, I forgot to mention earlier on about the element with the greatest ionization energy. And that is, remember, ionization energy was the energy required to lose the most loosely held electron. And the electrons in the outermost energy level. In this case, helium will be the element with the highest ionization energy. And I forgot to mention that before, so please make a note of that. And it's the same trend. If you look closer to helium, the greater the ionization energy is going to have. Because remember, helium would only have one energy level. And you have 2 electrons in that one energy level. So it's filled. It's very stable there. And they're very, very close to the nucleus. So they don't want to lose those 2 electrons, or that any one electron there. So you're going to have a higher effective nuclear charge. You're going to have a strong pull on those electrons. Okay. So here we're going to talk about bond type. Use electronegativity to determine bond type. So the difference in electronegativity, and that is the difference in electronegativity of the elements that make up the compound. We have not talked about bonds yet, but we're going to introduce it here. Now, you're responsible for knowing this table, memorizing it. Notice that if the difference is greater than 0 but less than or equal to 0.4, it's going to be a nonpolar covalent. If the difference is greater than 0.4 but less than or equal to 1.67, it's going to be polar covalent. If the difference is greater than 1.67, it's going to be ionic. So what does covalent or ionic mean? If it's covalent, it's made up of 2 nonmetals. As we can see here, nonpolar covalent, 2 nonmetals. Polar covalent, 2 nonmetals. If it's ionic, it's made up of either a metal and a nonmetal, or a metal and a polyatomic ion. Remember, poly means multiple or many. Atomic meaning atom. So you can say multiple atoms or many atoms. So what does polar versus nonpolar? What does that mean? It all has to do with the electronegativity difference between the 2 elements in the compound. The greater the difference, it's going to make it polar. Because they share electrons, but some atoms with a higher electronegativity will pull the electrons closer to them, as in the case of oxygen and hydrogen. Oxygen has a higher electronegativity than hydrogen, and it's so much stronger that it pulls the electrons towards it. If it pulls the negatively charged electrons towards it, it has a slight negative charge. Hydrogen, the electrons are moving further away from hydrogen, so they will end up with a slight positive charge. It's not completely positive or negative, it's just a slight charge. So that creates a polar covalent compound. So think about it as being like on a pole. You have 2 distinct regions. So you have a negative region here, and we have a positive region here. When it's nonpolar covalent, they're shared almost equally. So there's a small difference between the electronegativities. So they're shared equally. We don't create any negative or positive regions. And as we can see here, non-polar. And in ionic, it's just having a metal bonded to a non-metal or metal to a polyatomic ion. Notes, you'll see this chart that's similar to this. Now, you're not responsible for remembering these values. We just have this here so you can use it. But you will not be responsible for memorizing these. You'll be given that on your questions and so. But you're given two examples there. We want to find the bond type that exists between sodium and chlorine, all right, in sodium chloride. So first we find you're given a value of 0.96 for sodium. Well, I have 0.93 here, but we're going to use your values. And you're given 3.00 for chlorine. I have 3.16, but we're going to go with your values. So for sodium and chlorine, all you have to do is find the difference between these two. So chlorine is 3.00 and sodium is what? 0.96. So find the difference between these two. So you're going to do 3.00 minus 0.96, and that gives you 2.04. As you can see, that difference is greater than 1.67. So that makes it ionic because it's greater than 1.67. Now, look at the bond type that exists in the O2 molecule. Remember, O2, diatomic molecule. I bring clay for our new house, those diatomic molecules. You're given 3.3 minus 3.3. So that is 0. If it's 0, what's the difference we said? 0. So the electronegativity, the bond type, sorry, will be nonpolar covalent. Now, some of you will tend to write nonpolar only. You cannot do that. It has to be nonpolar covalent. Okay, so make sure you specify that it's nonpolar covalent. So you can do one. Let's do one more that's not on your notes. Let's do between, let's say, potassium and sulfur. So potassium is 2.58. So that is 2.58. And you're going to minus, did I say potassium? Sorry. Sulfur is 2.58 and potassium is 0.82. So sulfur is 2.58, potassium is 0.82. So 2.58 minus 0.82, that gives us 1.76. Okay, so if it's 1.76, that is greater than 1.67. So that means potassium and sulfur will form an ionic compound, or they will have an ionic bond. Okay, so let's talk about reactivity here. Metals. From all that we've seen, metals tend to lose electrons, not so? When they lose electrons, they acquire more positive than negative charges, so they end up with a positive charge. So think about the reactivity. Reactivity is going to increase in this direction. Why? Because we have atomic, this has to do with atomic and ionic radius. Again, atomic and ionic radius. So atomic and ionic radius, remember, they tend to increase in this general direction. If they increase in this general direction for metals, then they're going to lose those electrons easier. It's easier to lose those electrons. So the reactivity will increase because it's easier to lose those electrons. Now let's look at nonmetals. Nonmetals tend to what? Gain. They will tend to gain electrons. If they gain electrons, they gain negative charge. So they have more negative than positive charges. So they'll form a negative charge. And their reactivity increases in this general direction because we have higher ionization energy and higher electronegativity. It's harder to lose an electron and they have a stronger pull on the electrons. So that's what we're looking at here. Okay, ionization energy increases As you go in this direction from left to right for nonmetals, electronegativity increases as you go up. So that's what you need to look at. Okay, so let's summarize metallic character. That is a combination of reactivity of metals and the reactivity of nonmetals. Now, as you go down the group, the reactivity of metals increases. As you go from left to right, from right to left, sorry, the reactivity of metals also increase. They increase because we have a large radius. Okay, and that is in the neutral atom itself. They also have a low electronegativity. Whereas for nonmetals, we have a small radius, high electronegativity. So nonmetals have small radius with high electronegativity. So that for the metals now, this element here, francium, is the most reactive metal. For the nonmetals, fluorine is the most reactive nonmetal. All right. So that takes us to the end of periodic trends. We've looked at atomic radius, ionic radius. We've also looked at electronegativity, ionization energy, reactivity. So go through the video as many times as you need to, get the notes, have your questions ready, write down the questions that you may have, bring them with you to class or to tutoring so we can get them answered. So until the next time, I'm out. Blessings.